so the title kind of speaks for itself. Randomized online matching in regular graphs. Presumably we all know what matchings are. Let's maybe talk about the online matching. So I apologize in advance, a bunch of you know this pretty well. I'll try and go through the introduction moderately fast. So the input for the online matching, the underlying input is a bipartite graph. The left side or offline nodes are known ahead of time, and the online nodes, the right side or online nodes arrive online. And an online matching algorithm is tasked with matching arriving vertices immediately and irrevocably, or maybe deciding not to match. So for example, say the first online node shows up, it neighbors the first, second, and fourth offline nodes, and say we match it to the second offline vertex. So then the second online node shows up, neighbors 2, 3, and 4, and say we match it to 4. And say if the third online vertex shows up and only neighbors the fourth offline vertex, well, it's sad because it can't get matched to it. As usual, our measure of success will be the competitive ratio, which is simply the competitive ratio of an algorithm is simply the expected gain of the algorithm over an input over the optimum gain. Okay, so for example, if the algorithm that gave us this input were deterministic, the competitive ratio of this algorithm is clearly at most 2/3, because this input opt is easily shown to be 3, and the algorithm only got 2. Okay, and to make discussion a bit faster later on, we'll say if the competitive ratio of an algorithm is alpha, we'll say it's alpha competitive. Okay, so far it's very standard. We're clear on the algorithmic problem, right? Okay, so let's maybe start considering some algorithms for the problem. So first of all, let's talk about deterministic algorithms. So the first deterministic algorithm you'd think of for this problem, and indeed for anything, is just greedy, which in this terminology is exactly equal to match each online vertex to some arbitrary unmatched neighbor. Okay, so this clearly outputs a maximal matching, so it's at least 1/2 competitive. And unfortunately, no deterministic algorithm can be better than 1/2 competitive, as the following very simple example shows. So say one online node shows up, neighbors 2 offline vertices. Without loss of generality, the deterministic algorithm matches along the diagonal. And now an online node shows up and is only interested in the one matched. And of course, you can extend this to arbitrary large inputs. So 1/2 is really the answer. What about randomized algorithms? So the first random algorithm you think about is just matched to some uniformly at random chosen, some unmatched neighbor chosen uniformly at random. So again, this is at least 1/2 competitive, and unfortunately, it's not much better. We can show that this is 1/2 plus little order 1 competitive. For example, the following inputs. You have n online vertices and n offline vertices. Every online vertex neighbors an offline vertex just in front of it, and the first n/2 online vertices are connected to all the last n/2 offline vertices. So what you kind of expect is pretty much each of the first n/2 online vertices will get matched incorrectly across this complete bipartite graph. We get the matching more or less like this. Right? So most of the last n/2 online vertices don't get matched, and you can formalize this, but it's not particularly important for this. All right, so that doesn't work. Uncorrelated randomness doesn't seem to cut it. What about correlated randomness? So here comes the algorithm of Karp, Vazirani, and Vazirani, which introduced this problem of online matching. And their algorithm ranking works as follows. On initialization, you pick a uniformly chosen permutation of the offline vertices, like so. And whenever an online node shows up, you match it to its unmatched neighbor, minimizing the value under this permutation. Okay, so for the example that we gave earlier, it's not too hard to show that after you've seen a constant fraction of the first n/2 online vertices, their correct neighbor should have a lower value under the permutation than this, their correct match, quote unquote. Right? The guy just in front of them, over here, should have a lower value under the permutation than the unmatched guys at the bottom. Should have some value like theta. If you didn't follow that, don't worry about it. Not at all important for the talk. It's just to kind of give some intuition that this should at least help against these hard instances for random. And what Karp, Vazirani, and Vazirani in many future papers later on showed is that the ranking algorithm is 1 minus 1 over E competitive. Okay, where 1 minus 1 over E is 0.6. Right, so we have some lift over 1/2. That's nice. Could we hope to do any better? And well, Karp, Vazirani, and Vazirani showed that indeed you can't. Right? 1 minus 1 over E is the answer. So at least for worst case analysis, we understand this problem well. There's not much more to talk about. Fortunately, there's other things we can talk about. So we still have things to talk about. Okay. So 1 minus 1 over E, as I said, is nice, but you might be interested in more. And in 2005, Meta, Sadeh, Vazirani, and Vazirani related online matching and its extensions to internet advertising in kind of a natural way. So the offline nodes are advertisers, the online nodes are ad slots. Every impression is allowed to be shown one ad. Maybe advertisers don't have a matching constraint, maybe they have a budget constraint, but you can think about it as some kind of generalization of the matching constraints. And I guess if you're interested in working on online matching, this is great news because, as I'm sure it's not news to anybody here, online internet advertising is big bucks. So if you're looking to have your theoretical research funded, that's maybe a nice problem to look at. And a bit more seriously, so what Meta et al. Showed, and a lot of subsequent work showed, is that the 1 minus 1 over E bound is prevalent in many generalizations of online matching. So vertex-weighted matching, the AdWords problem was small bids, the display ads problem was large capacities, and so on and so forth. So if this is the optimal bound, then what more could we possibly be interested in? Well, just given the previous slides, 1 over E, or 36% of $60 billion is a lot of money, so saying this is the worst case optimal is not a good answer. Right, so this has pushed a lot of researchers to look into more practical, quote-unquote, inputs. So a lot of this research has been around stochastic assumptions. Maybe the input is drawn from some distribution, known or unknown, or it's some randomly permuted input. And for these, we know that we can get better than 1 minus 1 over E competitive ratio, even for the online matching problem. But you can't get arbitrarily close to 1, at least for the online matching problem. Generalizations, some generalizations allow better bound, but online matching, you can't get arbitrarily close to 1. Another vein of attack, which is a bit closer to what I'll talk about today, is structural assumptions. Maybe assuming that ad slots, not every impression is of interest to all the advertisers. Maybe advertisers are interested in large segments of the population, so on and so forth. All right, so that's my one slide about the practical aspects. Let's maybe talk about something very theoretical, which will be most of what we'll talk about today. So what we consider in this work is D-regular graphs. So these are graphs in which every node neighbors exactly D neighbors. So the number of online and offline vertices is exactly the same. We'll denote that by n. And an easy corollary of Hall's theorem is that such a graph has a perfect match. You can match every single vertex. And well, these inputs have been studied a lot in theoretical computer science, starting with research on regular graphs, work with Koenig and Frobenius, and okay, I won't bore you with too much name dropping. And it's been of interest for a lot of problems in DCS, not just matching, but since we're talking about matching today, let me just maybe tell you a little bit about it. So in the offline model, we know how to compute perfect matching in a bipartite regular graph in linear time, deterministically. And we can actually even do it in sublinear time randomly, okay, without even reading the input. And both of these results should be contrasted with the state-of-the-art max matching algorithms for general bipartite graphs that are all polynomially slower than linear.
GKK is
Grelica, Prarov, and Kahn.
Maybe people are not familiar. So I think sublinear is just ON.
Sublinear here was n log n. So if n is the number of edges, you can do like quasi-linear in the number of vertices. So if the graph is dense, I don't care about most of it. It's basically what they're saying. So all this is good news. I mean, I'm not going to talk to you too much about applications of bipartite of matching in bipartite regular graphs, but it does have quite a bit of applications, and the fact that you can solve that faster than for general bipartite graphs is great news. And the question is whether or not you could do something similar in online matching. Not necessarily because of any applications, just because it's a clean theoretical. All right, so what's known in online matching? So in recent work with Sefino, I showed that the optimal competitive ratio for deterministic algorithms on d-regular graphs is, ignore the exact expression, strictly greater than 1 minus 1 over b for any fixed regularity d. So a bit of contrast with what we said so far. For general graphs, you can't beat 1 minus 1 over e even deterministically. For regular graphs, you can do better deterministically.
No, but for general degree bounded graphs, do we know better?
I
mean, it's a bit of an unfair comparison because for increasing d, you actually get back to 1 minus 1.
Yeah. Okay. So that's good. That's exactly what I was just getting at afterwards. So as d increases, all right, it's nice, but doesn't seem to give us much. Another point of comparison, which we didn't discuss earlier. So for stochastic arrivals on regular graphs, so this does seem like a fair comparison now. Random and ranking are 1 minus order 1 over square root of d competitive. So not both. Random is good for the IID model, and ranking is good for the random permutation model. Whatever. All I'm saying is some simple randomized algorithms studied before are 10 to 1 as d increases, which is exactly what I'm saying here. So at least for stochastic arrivals, the problem gets easier as d increases. And the natural question is, what can randomized algorithms do under adversarial array? Okay, so deterministic algorithms, the problem gets inherently harder as d increases. What can we say about randomized algorithms?
So the last bullet over there with the 1 over square root d.
Yes.
Are you referring to the one with the disjoint?
Yes, I am.
Actually,
I'm glad you brought that up, because that paper basically showed that having a lot of large disjoint matchings is enough in the random order model. And we showed, by the way, that that's not the case for adversarial, right? You can just extend the KVB harnessing. I'd be happy to talk about that offline. All right, so we're clear on the problem. Let me tell you, not keep you in suspense for too long. So what we did is we presented a new randomized algorithm, which on d-regular graphs is 1 minus order square root log d over square root of d competitive. So up to the square root log d term, this matches the results known for random arrival models. Also want to say, so it also shows that the problem is actually easier, even in the adversarial arrival model, as d increases. We also get this or similar bounds with high probability, which is, best of our knowledge, the first at least observed high probability result for online matching. And we also give some kind of fairness guarantee where we can match every vertex with, ignore the exact expression, but something tending to 1 as the increases. Good, so those are the positive results. On the hardness side, we show that our results are nearly tight. So no algorithm is better than 1 minus order 1 over square root of d competitive. So again, up to the square root log d, this is the right answer. And another tiny bit of our hardness results, well, not like hardness per se, ranking and random are constant competitive, even as d tends to infinity. So we actually needed to come up with a new algorithm. We can just use something off the shelf. Any questions about the results?
So is it sufficient to assume that every vertex has degree at least d?
At least d.
Do you need d?
So we don't actually need d regular per se. We need some.
You need d disjoint matchings?
No, that's actually not enough to get something
But
close to
not
one.
enough.
That's not enough. Yeah. So my tangent earlier was Arniak. So I'd be happy to talk a little bit more. Maybe afterwards, I'll try and kind of hint at what are the general conditions we need. I mean, it's more general than what I'm going to talk about today. But all right, so let me maybe try and kind of hint at our general approach. So the first thing we'd like to do is match each edge with probability roughly 1 over d. This is the optimal fractional solution. And Well, our hardness result shows that we can't get exactly 1 over d, because that would give us a one competitive algorithm contradicting our lower bound. This is still the general direction we have to go if we want to get something tending to 1. So I'll try and kind of motivate that claim. So first of all, clearly, if edges are matched much less than 1 over d on average, then you're dead in the water, right? You're not going to get something tending to 1. So that's kind of a natural hope. On the other hand, if a lot of edges are matched more than 1 over d on average, then you'll have a bunch of vertices. You can have a bunch of vertices that are matched more than their degree over d, with probability more than their degree over d, and then I could just put all of those to neighbor the same online vertices. And then those online vertices have a good chance of not getting matched. All right, so that's a general hope. So let me maybe try and talk about some challenges towards this general direction. Maybe let me do some notation before, otherwise won't quite understand each other. So first of all, we'll have f of t denote the set of free, that is unmatched offline vertices at time t. FTI will be an indicator for whether or not the offline vertex I is free at time t. And the one thing that might be a bit, okay, anyway, DTI will be the degree of offline vertex I before the arrival of online vertex t, or before time t. Okay, so for example, at the beginning, before the input, the online vertices show up, DTI is, I guess you could say 0, it's undefined. When the first online vertex shows up, DTI of everyone is 0, because they didn't have any neighbors beforehand. After the second online vertex shows up, all the neighbors of the first have DTI 1. After the third one shows up, all the guys who had 2 neighbors have degree 2, all of those have. Okay, so relation should be clear. Okay, one more thing. And I'll abuse notation every so often and just have probability of x be the probability that x equals 1 for indicator variables. Just a small space saving trick. Good. So now let's maybe talk about some challenges towards getting this 1 over d marginal probability.
Just a couple of questions before that. So, another algorithm based on this intuition would be just match it to the one which has the highest degree so far.
So the highest degree so far, deterministically, because that's
and that doesn't work.
That doesn't work. Sure. Even matching, maybe picking uniformly amongst the highest degrees. But there's a family of algorithms. I'd be happy to tell you that we killed while looking for this.
Thanks.
All right, so let's consider the following input. This is again not so much analysis, just kind of getting some intuition as to what are the difficulties we have to overcome. So imagine you have an online vertex T, which has, of course, D neighbors, since we're looking at D regular graphs. Half of its neighbors have DTI equals 0, so T is their first ever neighbor. And the other half have also, sorry, the guys with DTI 0 we'll call low degree. I don't know why I'm using the clicker. The guy with low degree we'll call low degree neighbors, and guys whose degree was, sorry, D over 2 neighbors so far we'll call high degree neighbors. And ignore this matched earlier independently point, I'll get back to that. Okay, so what are some challenges, at least of the random algorithm? Well, if all the edges before time t are matched with probability roughly 1 over d, then all of these d over 2 high degree neighbors should be matched with probability roughly 1/2 before t showed up. Right? So that means that the observed unmatched neighborhood of t contains 3d over 4 guys, right? D over 4 of them should be matched. And here I'm saying, I'm using the fact that I assume they were matched independently before, so this should also be highly concentrated. So the probability of a low degree neighbor to get matched to t is exactly 1 over the degree of t, which will be just too high. Okay, so at least as far as our general guiding intuition. Fortunately, we can fix this, at least this example, relatively easily. I'll go into that really quickly. So what we'll do is we'll give each of t's free neighbors a weight, either 1 if you're a low degree neighbor, or 2 if you're a high degree neighbor and were not matched before. Right? Free. And then what we'll do is we'll match t to a neighbor I with probability proportional to its weight. Okay, WT will just be the sum of these weights. Good. And then, I mean, the probability of a low-degree neighbor, it's easy to verify. We should have high concentration of sum of weights, should be D, or around D was a high concentration, and therefore the probability of a low-degree neighbor and also a high-degree neighbor to get matched should be roughly 1. Good. So that's at least part of the general approach. What am I overlooking here? So this is basically our approach. So if T has a bunch of free neighbors, every free neighbor I will have a weight which is inversely proportional to its probability of being free at time t. So its expected weight should be exactly 1. And again, we'll match T to neighbor I with probability WTI over sum of the weights. And as I was saying, the rough intuition, since the expected weight of any particular vertex neighbor is 1, the expectation of the sum of the weights is too fast. So WTI we said is 1 over the probability, and we'll give this weight only if it's free. So with this probability, so this term cancels out. We have D neighbors, so this is sum of the weights. An expectation at least is D. So a quick moment of suspense of disbelief. If the sum of the weights were exactly its expectation, then for every neighbor of T, the probability of this neighbor I being matched to T is exactly its weight over D times the probability that it wasn't matched before, which would be exactly 1 over D. Of course, assuming that the random variable is always its expectation is a bit of a stretch, so let's maybe see what we should actually be saying here. So this is, I'm just repeating the analysis here. Okay, so as we said, we'll try and match neighbors of T with probability proportional to their weight, which would be 1 over the probability of those guys being free times the sum of the weights. And the problem is that since the sum of weights can deviate from its expectation, we have 2 possible problematic cases. The first is if the sum of weights is below its expectation, we'll match the neighbors of T with too high a probability. And on the other hand, exactly the same thing. If the sum of the weights is too high, we'll get matched with too low a probability. And actually, the second case is the particularly problematic one, especially if you account for possible positive correlations. Right? If my probability of being unmatched means that a lot of other guys are likely unmatched, then I'll very often be on this side of the bell curve. And then maybe I'll get too low a probability of getting matched at any point. And that should only kind of be a vicious cycle, right? I was likelier to not get matched before, I'll again be likely, and so on and so forth. Okay, so how do we overcome this problem? Well, the general approach is, first of all, if the sum of the weights is below its expectation, just don't match with some probability. That's kind of an easy fix, right? With some probability, just decide, okay, I'll ignore T. I'm not going to be a maximal matching. I'll ignore T, and hopefully I'll be able to show that the loss incurred by ignoring some online vertices won't be too problematic. So that part hopefully should be obvious enough. The second part is, if the sum of the weights is too high, right, every vertex has too low of a probability of getting matched, we'll match some extra vertices. Now, this means absolutely nothing, right? But I guess that just means we'll mark these extra vertices and say, look, from now on, I'm not going to actually match. And hopefully here again, the fact that we're not maximal will not harm us too much, and as we'll see. Are we okay with the general approach? So a quick recap of the approach. We want to match each edge with probability roughly 1 over D. So what we'll do is we'll mark each edge with probability exactly 1 over D, such that all the matched vertices are marked, and most of the marked vertices are actually also matched. So sorry, I said I'm marking edges. Marking a vertex just means it has an edge incident on it that's marked.
If you mark an edge,
if I mark an edge, that vertex is out.
Offline vertex is out.
Okay. Right, so in two ways we're not being maximal. We're ignoring some online vertices with some probability. Some of their weights are too low, and we're just ignoring some offline vertices, also kind of not through any fault of their own, if the sum of the weights is too high. Okay, and this is just what I said. Right, so quick recap of notation. It's going to be pretty much what we said before, just a slight modification of one thing. So ft will be the set of free, but this time free means unmarked, vertices at time t. Fti as before is an indicator for whether or not you're free at time t, dti is a degree at time t, and delta ti will be the residual degree at time t. So here we know that the graph is regular, and therefore we can compute this ahead of time. We have more general things that I was saying earlier, which we'll get now. Good. Now, without further ado, here's the algorithm. So our algorithm, which we call marking, works as follows. For each online vertex t, we look at each of its neighbors, I, and we give it the weight d over the residual degree of I at time t times the indicator for whether or not it's free at time t. Okay. And we'll get to where this expression comes from, but we basically went over it earlier, so soon we'll see that's the same position. And then, as I said earlier, with some probability we might not actually match t to anyone. So with probability, the minimum of sum of weights over d at 1. Remember that the expected sum of weights was d, so if we're exactly expectation, we'd match t every time, but if it's below, then maybe we'll ignore t with some probability. In that case, we match t to some node chosen with probability proportional to its weight and mark that node. And finally, the sum of the weights, so this is the left side of the bell curve in our intuition for the solution earlier. And for the right side of the bell curve, if the sum of the weights is higher than its expectation, we'll mark each offline neighbor of t with some probability. Don't worry about the exact expression, it's just something to make the terms work out.
So in the case where w by d is greater than 1, you still match.
I still match.
But then you mark a few more.
But then I also kind of burn off a few offline vertices.
So what is the probability that how should I think of these marking probabilities at the end?
They're just something to make the marginal probability of getting marked exactly your weights.
So you're marking with probability. Okay.
Yeah.
Right.
Okay.
So as the algorithm unfolds, like various off-mean things might happen.
Right.
And he's correcting them by.
Yeah, so here I'm just making sure that you're always exactly on the mean. At least the probability of getting marked is exactly its expectation.
So in expectation, you'll exactly make it d after that step.
Yeah. Sorry again.
The sum of the weights.
Yeah.
Before the arrival of the next vertex will be exactly d for
exactly.
So after every correction, when you do some extra marking, then it's a guarantee that the next vertex will see.
In expectation.
In expectation. So this is basically the choice of the weights is exactly.
No, not the next vertex. The current vertex that you just saw, it's expected. The expected weight of its unmarked neighbors will become d. Is that right?
The expected should be d minus 1, right? So you're marking one node in expectation. Maybe you're not marking in some cases, and maybe you're marking a few in some other cases. But since you'll mark each with exactly probability 1 over d, in expectation you're marking 1. Right? So you're decreasing the number of unmarked vertices by 1 in expectation. Good. Okay, so I've hand waved my hands enough so far. So let me maybe try and give you some ideas of the analysis. So the algorithm, this is the same algorithm as before, just put it on the right so it doesn't take up too much space. So here's the general idea for the analysis. So first of all, we're going to bound the probability of an online node T not being matched in terms of the sums of weights. And that'll be this lemma. We'll get to that in a bit, but this should actually kind of be obvious from what we said so far, and if not, we'll show it shortly. So the probability of T not being matched is just the standard deviation of the sum of the weights neighboring it over D. It's at most that maybe over 2. Good. So in order to bound the average standard deviation WT, so we could get a bound on the sum of the expected unmatched online vertices, which correspond exactly to our competitive ratio. We'll bound the variance of every single weight. And then we'll show a negative correlation between the weights, and then we should basically. All right. Any questions about the general approach? Right. So first, maybe last notation. MIT is going to be an indicator for edge IT being marked. So I want this probability, the probability of MIT, to be exactly 1 over D. So that's what the first lemma says. And the first corollary of that is that the probability of I being free at time t is its residual degree over D. Right? It starts at 1, and every time it sees another neighbor, its probability of being unmarked decreases by 1 over D, which is exactly what's written here. And why is that important? Well, that kind of relates to our intuition from earlier. That means that this D over delta Ti normalizing term is exactly 1 over the probability of I being free at time t. And therefore, the expected weight of any particular edge is exactly 1. And kind of all the intuitions we said so far will kind of will guide our analysis. Good. So how do we prove this? So this is an easy proof by induction. So for any set of unmatched vertices A, including I, the probability of the edge IT being marked, conditioned on A being the set of unmarked vertices at time t, I claim is exactly the weight of the edge I divided by D, which is exactly 1 over the residual D. So I won't prove this for both cases. Let's just consider the one case where the sum of the weights is less than its expectation. Sorry. In the other case, as I said, the numbers are just there to kind of make things work out. So if the sum of the weights is less than D, what's the probability of T getting matched and marking someone? It's exactly sum of the weights over D. And any particular vertex is marked with probability proportional to this, so everything cancels out. Exactly what you want. Good. And now we just need to condition, right? So the probability for any particular, the probability of the edge IT being marked conditioned on I being free at time t is exactly the expression above. Right? For every one of the the possible sets A, that's the case. And therefore, the probability of MIT of I being marked at time t is exactly the conditional probability times that the probability of the condition, and plugging in the inductive hypothesis in the previous expression, we get exactly that. Okay, so that's the first lemma. This is that was our initial motivation, right? We wanted every edge to be matched with probability 1 over D. That seems like a bit of a stretch. So at least we want every edge to be marked with probability 1 over D. Okay. So a few consequences of this. So if the probability of I being free at time t is exactly its residual degree over D, then that means that the expected weight is exactly 1. Same thing we said before, right? This D over delta Ti is 1 over the probability of being free. And there's a corollary, the expected sum of weights is exactly D, again, as with our motivating examples. And another thing we'll need is, okay, so that's first moment. What about variance? Well, the WTIs are just scaled Bernoulli variables, right? So variance scales quadratically, so this is, the expression you have here is the variance, right? It's this D over delta Ti term squared times the probability of being free, cancels things out, you get exactly D over delta Ti. And from this we find that for any offline vertex I, the sum over all of I's neighbors of the variances of I's edges is exactly order D log D. It's just D times the Dth harmonic number. Okay. Push that on the stack, we'll get back to it later. All right, so we've got some overall bound on the variances. How can we use that in a more local way? So as we said while discussing the roadmap, the claim is that for every online vertex t, the probability of t not being matched is at most the standard deviation of wt over d. And this, this is kind of easy given the things we've seen in the previous slide, so let's do it quickly. The probability of t not being matched is exactly the probability that it's 1 minus wt over d. Right? If you're below your expectation, it's just by how much you deviate. Right? So taking out absolute values and remembering that the expectation of wt is d, and maybe taking out square root and squaring things, line ends and ones, what we get is, as I claimed, that this expression is at most the standard deviation of wt over d. If you didn't follow this, there's really nothing very deep going on. It's just saying that the expected deviation from your expectation is at most standard deviation.
So I kind of follow the math, but is there an intuitive way of understanding why in the process t not being matched depends on the variance of the weights around t?
Well, wt is just the sum of these weights, right?
Yeah.
So it does depend on these weights. Right. Here I'm just saying it depends on the sum of the weights, and shortly we'll show that you can bound the variance of the sum by just the sum of the variances.
Okay.
Okay, so that actually kind of leads to the next slide. So I'd like to be able to bound this variance of wt, right? So variance of sum wti by something depending on the sum of the variances of the wti's. And for that, we're going to have to rely on the following toolkit. If you've never seen this before, this is a good time to zone back in. This is a nice toolkit to use. It's very useful for a bunch of balls and bins results. It kind of simplifies a lot of known results, and sometimes it gives some other things. So I'm going to try and do like a 1.5 to 2 minute primer on negative association. So the definition is pretty intuitive. We say that n variables x1 through xn are negatively associated. If for all monotone increasing functions f and g, the functions f of x, depending on disjoint xi's, the functions f of x and g of x are negatively correlated. I'm saying that's very intuitive. Maybe the way I stated it isn't. I'm just saying that look at these variables, and if I tell you, look, these guys are relatively large for any way I'd like to measure large, then in expectation these guys are small. Again, for any way I'd like to measure, right? So for any f and for any g. Okay. So why are these useful? Let me maybe give you a bunch of examples. Can anybody give me an example of such a family, such a distribution, like off the top of their head? A trivial one. It doesn't have to be particularly interesting. Independent variable, right? So that's not very exciting, but okay, one example. So at least you can expect to maybe get things that you can get for independent variables. A slightly more interesting example is what's called the 0-1 lemma. So we have a bunch of binary variables, x1 through xn, whose sum is always at most 1, then they're clearly negatively associated. Right?
For any threshold, any bound.
Not for any bound. So for example, if I tell you that the sum of these guys is always 2, then notice that this the definition of negative association also implies pairwise negative correlation. I just take f and g to be like xi and xj. Right? Now if I have so I have n variables, I just say have either x1 and x2 be 1, or x3 and x4 be 1, or 5 or 6 be 1, and so on and so forth. And clearly I don't have negative correlation there, right? If one of those two is 1, then the other is 1. It's probability 1. Does that make sense?
I was going to say at most.
Oh, at most, no. So again, this example it could be like sharp. It's always 2, right? If I start off with n variables, right, and now I just couple them in whatever way I want, it'll always be at most 2 of them that are set. And so that would be a really nice result, but I suspect you'd be able to prove some unreasonable things.
So sorry, I guess I missed that. So you take independent and you condition on the fact that they're at most k.
Independent at most k, yes.
But then they will be.
Yeah.
Sorry, I missed that. You're not enforcing.
I'm not conditioning on anything. I'm just saying. So this is a much simpler scenario than you're describing, right? So if I tell you they're all zeros or ones, and maybe one of them is one, if these are large, one somewhere here, right? All right. So these are some simple examples. Not quite clear you can do anything useful with that. But what's nice about negative association is that you also have closure properties, so you can get some more interesting distributions from that. So for example, the union of independent negatively associated distributions is itself negatively associated, and follows easily from definition. And another useful property is that if you have a bunch of monotone increasing functions, depending on disjoint variables, then these functions applied to x, their outputs are themselves negatively associated. So for the tagline you're looking for here is calculation-free proofs. It's very, well, I guess it's an appealing property if you want to check something quickly without thinking. So why would we actually be interested in these NA distributions? Well, some other useful properties are, as we mentioned earlier, they're pairwise negatively correlated. That's easy. And actually, a bunch of bounds that we like to apply to independent variables apply to this much wider family of distributions. Okay, so for example, Chernoff-Hopning bounds, and okay. All right, so in 2 minutes, it's kind of hard to do this topic justice. So if you're looking for, independent or better is the second tagline. So if you're looking for sources for this, I have some notes online. I guess there are a bunch of notes. Okay, so back to our regular programming, quote unquote. How are we going to use this negative association? In a kind of simple way. So the claim is that the variables MIT, again, indicators for whether or not the edge IT is marked, conditioned on any set of free vertices, are negatively associated. And given the previous slide, this will be a really fast and simple proof. So conditioned on this set of free vertices.
So this is for a fixed t, so MIT for a fixed t.
For a fixed t and for a fixed set of free vertices. Okay, so first of all, we'll have the first variables that are one if I was marked by this vertex because I was also matched this vertex. So clearly at most one of these happens. So 0, 1 lemma says they're an A. Second set of variables are all these independent coin tosses at the end. And whether or not you're matched is just, so these are independent distributions, so their union is NA. And now whether or not you're marked is just the OR of two variables, right? MIT depends on two variables that no one else depends on for any fixed INT. And so these MITs are themselves NA, right? Just by applying the second closure property. That's it. There's really pretty much nothing to show here. If I had a bit more time, I'd tell you how much calculation and futile work this saved. Maybe. Okay, so why is this useful? So I claim that this in particular tells us that the covariance, that the indicators FTI and FTJ are negatively associated, very fixed T and INJ. I'll show that in a minute. And why is that useful? Well, the weights WTI and WTJ are just scaled values, scaled versions of these FTI and FTJs. So they're negatively associated. Negatively correlated. Getting ahead of myself. In which case we can just apply subadditivity of negatively correlated variance of negatively correlated variables, and therefore the variance of WT is at most the sum of the variances of WTIs, which is kind of what we were expecting, at least hoping. For time, good. Let me convince you of this fact. So as I said, the covariance of FTI and FTJ is at most 0. So this, again, is an easy proof by induction, so let's go through it. For step T, if I and J, T plus 1, if I and J are neighbors of T, then the probability that I is free by time T plus 1 is the probability that it was free by time T and that it was not marked at time T. Right, so that's probability not marked at time with this. Probability it wasn't marked at time T, conditional on it not being marked before, times the probability of it being free until then. From what we showed earlier, this expression should be exactly 1 minus 1 over delta Ti. showed for any conditioning that this is the case, times probability of being free. And now let's look at any pair. The probability of the pair not being matched, not being marked, sorry, is, I mean, it's the same argument, right? They both need to not be marked at time t, and they both need to be free at time t. So plugging in the inductive hypothesis and the negative association, the probability of both of these not being marked by negative association is at most the product of the individual probabilities. So that kind of explains why I'm replacing this expression by these two guys. Okay, and the second inequality is from the inductive hypothesis, and then all right. So now I claim we've pretty much got everything we need. Let me do like one more slide of calculations, and then we're basically there. So finally, I claim that the sum of the variances of the WTs is at most order of n times square root d log d. If you remember how we bounded the probability of a particular vertex not being matched, this will relate to our loss, but let's not get ahead of ourselves. So the sum of the variances from the previous slide, the one before that, is at most sum of the individual variances of the WTIs. Like we said, the WTIs are negatively correlated, and therefore sum over T of variance WTI is just sum over T, sum over I. Variance WTI. Rearranging a little, we find, I mean, I'm not doing anything here, I'm just rearranging our order of summation. And from corollary quite a while ago, we know that for any fixed I, the sum over all of I's neighbors, variance WTI, is order d log d, which is just n times order d log d, right? We've got n offline and n online vertices. So if we pick a random online vertex, its expected variance is order d log d. Finally, applying Jensen's inequality again, we find that the expected standard deviation of WT is at most order of square root d log d. And now we're basically done. So theorem, algorithm marking, run on d regular graphs, is 1 minus order square root log d over square root of d competitive. And the proof, so as I said, we already have all the ingredients. So what we said before our digression into negative association is that the algorithm's loss is just sum over all online vertices t, probability of t not being matched, which we said is at most the standard deviation of WT over d. By the previous slide, this is n times order square root d log d. Simplifying a little bit, this is our loss. Therefore, the algorithm's gain is at least n minus that expression. That's exactly what it is. All right, so we ended up with a little more calculation towards the end than really what everyone was happy with after lunch. So let me maybe just leave you with a summary slide of our results. So as I said, we have an algorithm that's 1 minus order square root log d over square root of d competitive, showing that the problem of matching, online matching in regular graphs, even in the adversarial model, is just becomes easier as d increases for randomized algorithms, whereas for deterministic algorithms it becomes harder. We have matching high probability results. You can guarantee every vertex probability that to 1 of getting matched. And our results are pretty much that's it for that one. Thank you for your time. Maybe I'd like to maybe get back to your question earlier about whether or not we need regularity. So what we've generally got here is an online dependent rounding scheme. You give me some fractional solution, which you can compute online. In this case, there's a very trivial one. 1 over d is an easy fractional solution. We show how to round this. Unfortunately, you can't do this in a lossless fashion, just because of our hardness results. But we can control the loss by a term which depends on the sum of L2 norms over sum of L1 norms of the vectors that correspond to the fractional solution for every online vertex. I'd like to have a nicer term for that than that. It's not exactly average L2 over average L1. That would have been nicer. I could have done something with that. So for example, what we can do is if all the degrees are between, say, d and d plus minus square root d log d, you get the same results. So that, for example, allows us to get online approximation algorithms for bipartite max matching in regular graphs, even faster than the Guelka-Pavlov-Encana, for example. The approximation would depend on how sparse. I mean, you just subsample the graph and just run this approach with the correct fractional solution. Right? So you'd sample. So every vertex has degree c, and you should get like a.
Sorry,
Okay, I don't want to catch I don't want to trip myself up over the exact expression. I think it should be like.
If you're going to output almost linear, at least if you're going to match at least n by 2 vertices and output them, you will need n by 2 time. So what does it mean to beat Guelka?
If come again?
I mean, their running time is
n log n.
right?
That's pretty fast. So I'm saying we can do if you're willing to get an approximate solution, you can do faster than n log n. And even in an online sense, like for example, if you start off with a regular graph, right? You go to d-regular graph. Okay, maybe I'm not willing to sample to compute something that depends on d values, right? So for example, for a more applied setting, if you're talking about online advertising, I don't want to look at all the advertisers that are interested in this particular ad slot. I sample C of them,
okay, and
I claim that you can still get a good solution.
Okay.
No patent on that, guys. So if you guys want to try it out and see if it's useful, let me know.
So if let's say this general graph, bipartite graph, and I gave you the fractional solution, offline fractional,
sure.
Then does this all work, or does it need some properties in the fractional solution, some constraints?
So in some sense, it needs. Yeah, we kind of need the values to give you something, right? Trying to think of. So again, the loss is in some sense determined by this by a function of the fractional solution. You can expect completely.
Because the variance depends on the
variance depends exactly on these values. Yeah. Yeah, I mean, we're looking at some extensions of this to see if, what else can be done with this approach. Will the story seem coherent enough where the variance is 1 over square root? So.
Thanks again, David.
Thanks.